Good morning, students. Today I am going to talk about Lagrangian of electromagnetic of a particle in an electromagnetic field. Now, for a free particle, the Lagrangian will be equals to kinetic energy. In classical mechanics, you already learned that Lagrangian equal to L equals to T minus B. So, in classical mechanics, well, you don't have to consider the Lorentz transformation. Then simply Lagrangian is the kinetic energy. But when we are considering the Lagrangian which has to be Lorentz invariant, we should consider proper motion or proper time such that the Lagrangian should be invariant. Now, as in the classical mechanics, the axle T1 to T2 L dt would be extrema, right? Now, this has to be changed to proper time, tau 1 to tau 2 gamma L theta, right? Because theta is dt equals to gamma into theta, and we have transformed tau 1 to tau. Now since theta is invariant under Lorentz transformation, so gamma L should be invariant under Lorentz transformation. Under Lorentz transformation, it should be invariant. Therefore, we propose L varies as 1 by gamma equals to root over 1 minus beta square. So the suggestion is for free particle Lagrangian, it should be minus m0 c square root over 1 minus beta square. This is the free particle Lagrangian. And based on this thing, let us check whether this Lagrangian that we have taken as a guesswork, whether this Lagrangian should produce correct equation of motion or not. Now we know Lagrange's equation of motion is that ddt of del L del T del L del U, I think, velocity. That will be equals to minus del L del X, but this thing is equal to 0. So this goes to 0. Right? Now del L del U will be equals to, therefore we say ddt of del L del U minus m0 c square. This goes down root over 1 minus beta square. Now beta square contains u square by c square. So 1/2 will be there. 1/2 will be there for this factor. And this will be minus twice u by c square. Right? This c square will go, this plus minus will go. So it will simply become this equals to gamma against. So this will be equals to ddt of gamma M0 gamma M0 U. I think gamma M0 U. So now gamma M0 is nothing but M, and gamma M0 U is momentum. So this is equals to ddt of T, that is equals to 0, which is Newton's laws of second law of motion. So in fact, this Lagrangian gives you correct equation of motion. This correct equation. So free Lagrangian is this. So one thing that we have learned, that the free Lagrangian which should be invariant under loading transformation will be m free will be equals to minus m0 square to the power 1 minus beta. So this is free Lagrangian. Now we have to consider potential energy. Again, we have to depend on guesswork. We know for static case, potential energy equals to Q into phi. Right? Potential energy V will be equals to Q into phi for static. For static electric field. Right? Now key charge phi is phi is the fourth component of potential. So we guess the potential energy will be of this form. In general, potential energy will be potential energy to Q by gamma C Q alpha A alpha. This will be the general form of potential energy. So if we work out, you have already U alpha equals to minus gamma U gamma C, and A alpha equals to CA phi, CA phi. So this thing will go gamma C. This can be written. This can be written actually as this can be written as 1 by gamma C into gamma C into phi. This can be written. So from this we suggest this will be the form. Now working out this thing in Q by gamma C U alpha, we are working out this thing minus gamma U gamma C, taking dot product of scalar product of phi, these two vectors give you gamma C. This will give you gamma C phi minus gamma C U, right? So this gamma C will cancel out. So this simply will be phi minus U. So this is the potential energy. Interaction potential energy. So now Lagrangian A equals to T minus V. Now T is L free equals to L free T is L3 minus D. So this comes out to be minus M0 square root over 1 minus beta square plus Q. This minus will go out if you write U dot of A. So this is the Lagrangian for a particle in an electromagnetic field is when you will again see it in your higher classes field theories, you have to use the Lagrangian of this form. Now I am leaving you as an exercise homework for you that whether this Lagrangian produces Lorentz force equation or not. Check. So check whether homework. Check L satisfies Lorentz equation. L satisfies Lorentz equation. You can check it. Lorentz force equation we have already derived. What is that? Lorentz force equation is dp mu tau is equal to q by c f mu. So this is Lorentz force equation. So if you use this Lagrangian here and then use your Lagrangian equation of mu, then you will get this thing. Provided you have to replace ddt with respect to del del d tau. And velocity is of course right. Now once we have formulated Lagrangian, our next task our next task will be to form to to write down or to evaluate the form of Hamilton. Once Lagrangian is done, we are left with Hamilton. Hamilton. Now we know conjugate momentum. We have conjugate momentum. We call PC conjugate momentum. PC, say I am taking X component. For this will be del L del UX, right? Del L del UX. Now from the form of L equals to minus M0 square root of our square plus U dot of A minus 1. This is the form. Now if you perform del L del UX, then it will be QX plus gamma M M0 UX. Del L del UX, we have already done it. So check del L, this differentiation with respect to UX will give you this thing. We have already done it. So conjugate momentum, this is nothing but momentum Ux gamma m equal to m and Ux this is equal to Px. Right? So conjugate momentum we can write Pc will be equal to Qa plus P. Right? So conjugate momentum will be this. Now we know Hamiltonian H will be equals to, you know, for a single particle there will be summation what? Pc dot of u minus L. Now, but we are considering for a single particle, the summation goes out. So Pc dot of u minus L. So this will be equals to P dot of u plus u dot of A. Right? Now write L minus m0 c square over 1 minus beta square minus u dot of A plus u5. But this thing will cancel. So this comes out to be P dot of u plus m0 c square by gamma. This term writing plus, so I am writing this will be plus m0 c square root over 1 minus beta square. So this is the Hamiltonian. Now this can be simplified in a compact. How? By seeing this. Now P dot of u, if you start from P dot of u, then this will be equals to gamma m0 u square. Gamma m0 u square. And this will be equals to m0 c square by gamma, right? Plus q. You can check it for yourself. P dot of u will be equal to gamma m0 u. P equals to gamma m0 u, and u is u, so gamma m0 u square. Very simple. So this will be now this can be written if you write u, work it out u. Then it will be Pc minus, it will be Pc minus Qa, and this P by gamma m0 p square by twice this form. You can write also plus this term is gamma c square by m0 c square by gamma plus q. Now take LCM. So this will be Pc minus Qa whole square plus m0 square c square by gamma m0. Now gamma m0 is nothing equal to m. Gamma m0 is m. So Pc minus Qa whole square plus m0 square c square by gamma m equal to m. M equals to E by c square equal to mc square. Now E by c square will be equals to E is nothing but p square c square plus m0 square is equal to 4 plus 2 4. So this will be equals to Pc minus Qa by 4 square, c square goes out, E equals to root over p square, p square c square, p square c square plus m0 square is equal to 4 plus 2. Now if we substitute p with Pc minus Qa, then this c square will be there. So it will be something like this. It will be there will be m0 square c square. So this calculation will come out to be root over c square pc minus qa, that whole square, plus m0 square c4 to the 4 plus m0 square c4 to the 4. This is square will go out, so this will be c4 to the 4, c4 to the 4 root over plus q4. So this will be the Hamiltonian. So H final form H will be equal to root over c square pc minus qa whole square plus m0 square c4. This will be the so Lagrangian and Hamiltonian formulation of particle in a electromagnetic field is complete. Now, when you will again you will study in your higher class field theory, you have to use this language, this type of Lagrangian, Hamiltonian. This Hamiltonian has to be used in field theory. So that is all about fields, electric and magnetic fields, and then their corresponding covariance formulation, and ultimately Lagrangian and Hamiltonian of free particle. Now field can also be Lagrangian and Hamiltonian formulation of the field itself, not the particle, can also be derived. So this topic, the covariance formulation of electrodynamics, is finished. Next, we have to go to the situation where we have derived Leonard-Wishart potential for a moving charge. For a moving charge, Leonard-Wishart potentials, that means scalar potential and vector potential for a moving charge, was derived, and we have seen that the potential for a static field, potential for a moving charge is increased or enhanced due to its motion compared to the fixed compared to the potential for static charge. Next, once we have obtained the expression for potential, now the expression for electric field and magnetic field is very easy. What you have to do, you know, E equal to minus grad phi minus del del t, V equals to del cross F. So what you have to do, you have to take derivative, gradient and curl and time derivative. You will get it. But there is problem here. As you have seen, you must have noticed that Leonard-Wishart potentials, the forms of the expression contains retarded terms. That means that expression must have evaluated in retarded time and position. Generally, what we do, the if potential for at a field point is known, then taking derivative both in space and time, you can get the fields. But here we have to transform this derivative into retarded time and positions, because field point is fixed but the particle is moving. Since the particle is moving, so we have to take derivatives changes with respect to retarded time and position. So that is the one subtle thing that has to work out. Once we have done that, then we can straightforward the straightforward equation for electric field. What are the expression for electric field and magnetic field? We had Leonard Richard potential, Leonard Richard potential of this form. Y equals to E by 4570 1 by R minus R dot of beta. That was the expression. We call this A by S. That S is this. A was this. A was mu 0 by 4 pi E by C beta by S. So that is equal to, we say, A by C beta by S. But this has to be evaluated at retarded time. This has to be evaluated at retarded time. Rate determines retarded time. These two things has to be evaluated at retarded time. Now you know E equals to minus that phi minus del del T. Right? And B equals to del cross of A. So you know phi, you know A, you can evaluate it. But one thing is that this differentiation is with respect to X. This is with respect to T. We have to transform this into X dash and T dash. So this is the thing. We have to make the change of differential derivatives. So to change the differentials, we have retarded time. Retarded time is given. T dash equals to T minus R by C. Right? So differentiating with respect to T. Differentiating with respect to T dash. 1 equals to del T dash minus 1 by C del R dash. Now del R del T dash has been evaluated. I have done it. So this will be equals to del T dash minus this will be equals to del R del T dash equals to R cap del R del T. Means R cap dot of. So this will be minus will be plus 1 by C R cap R cap dot of U. So this will gives you del T by del T dash 1 by U by C is beta. So R cap dot of because del R del T dash you can evaluate del R del T dash will be equals to minus C beta C R cap dot of. So del T by del T dash. So we can say del T by del T dash will be equals to 1 minus R cap dot of beta. We call this thing D. Say call this thing D. This is nothing but this is equal to S by R. Okay. This is nothing but S by R. Now we want to change the differential. Now we have from the first relation del T dash we have the relationship del R del T dash can be written as del R del T into del T dash del R del T del T del T dash del R del T. I'm sorry, del R del T will be del R del T dash by del T can be written. Now del T dash by del T is nothing 1 by D. So this will be equals to 1 by D del R del T dash. So in operator form, we can write del T will be equivalent to 1 by D del T dash. Right? So whenever we are doing del T, it must be read as 1 by D del T dash. So differential with respect to time or derivative with respect to time has been transformed. Now we are left with space derivative. That means del operator. Now for space derivative, you know R is function of R is function of R dash T dash, right? I mean R dash T dash. That R is function of this. This is also function of R also. So del X R, I denote del X R to be differentiation with respect to the field points. Del R will be equal to del X dash R differentiation with respect to source point plus del dash del X dash T dash, I'm sorry, del X T dash into del T dash del R del T dash. I mean, I have taken derivative of T dash. I have taken derivative of T dash and then leave it del R del T dash because T dash contains R dash also. Now we know this. So del T dash, this will be equal to del X dash R plus del X T dash. This is known minus C beta dot of R cap, right? Minus C beta R del T dash. This. Now there is a relation del T del T dash. Now there is a relation from retarded time. You can write T dash equals to T minus R by C. So del T dash will be equals to minus 1 by C del R with respect to X. That so del R will be equals to minus C into del T dash. So we write here minus C del X T dash will be equal to, this is nothing but R cap plus, I'm sorry, minus C beta dot of R cap. So you see del X T dash will come out to be R cap by C into D minus del X T dash is this. Now in terms of operators, del x t dash is this. Now in terms of operators, write this form. In terms of operators, del x r equals to del x dash r plus del x t dash, we write it here, minus r cap by cd, r cap by cd del t dash of r. So in operator form, this will be del x will be equals to del x dash minus r cap by cd del. This will be the operator form. So again we get a relation del x dash x will be equivalent to del x dash plus minus r cap by cd del t. So this is another order, right? Now we have transferred the differentials. Now we are left with calculation. Say, for example, I'll do it in the next class. Just I am showing it how to do it. E equals to minus grad phi minus delta delta. What will you do? Minus, this will be transferred as grad x dash phi plus r cap by cd del phi by del t dash, right? And this will be equals to minus 1 by d del a by s, right? Now the forms of phi, this, then a, this has to be written, and correspondingly that terms has to be, these terms has to be evaluated in proper form. So I think today up to this. In the next class, I will derive the expression for E and B. Notice that this expression will not be so easy, very tough expression. It will be better if you go through the uh, go if you do your calculation first hand in your own hand and see where are the difficulties. Then you will probably realize where. So we have this.